Oh, I have good news. I've just been notified on my YouTube page that I can now upload videos longer than 15 minutes. I must be a super user. Oh yeah. Um, but then I was thinking, would it be better to have, a bunch of shorter videos so that you guys didn't feel as overwhelmed that you had to watch like a 40-minute video or something? And then I was like, it might be actually better to have less videos on the page so it just didn't seem so overwhelming to find a video. And then, if you can't watch a video for 40 minutes straight, that's the beauty of having these on YouTube. You can stop and pause these anytime you want. If you have to go get a bite to eat or go, um, you know, take a trip to Negative Land or something, you can always pause the video and it's just as simple as making a quick note. All right, I made it to 14 minutes and 37 seconds. So I'll just continue from 14 minutes and 37 seconds next time I watch it. So I think I'm going to make my videos long and you can keep track of where you were and where you are in the video. Sound like a plan? Excellent. So, with my new power, I can feel less pressure to kind of get as much in 15 minutes as possible, and I like that freedom. So, in this video, I'm going to finish up the graphing motion aspect of things, and I'm going to do that by showing you the acceleration graphs. And I guess I could have drawn these earlier, but I don't know. I like drawing it while during the video. It gives you a chance to kind of slow down and process things, um, which is nice. If you're trying to keep up with every word I say and I'm just like plowing through and going topic after topic, it might be a little overwhelming. So, yeah, so I'll just take my time and draw these out. All right, let's see, let's start with this one. So, um, we discussed early in an earlier video that acceleration is how quickly how quickly velocity is changing. Okay, excuse me. Just as velocity is how quickly position is changing. So, thinking about how I worded that, you should, be able to reason that whatever we do going from this graph to this graph, whatever we do going from a position graph to a velocity graph, we can do the exact same thing going from a velocity graph to an acceleration graph. More specifically, whoops, more specifically, whatever the slope is of the velocity graph, that's going to give you your value for your acceleration graph. So let's do that for each of these graphs. All right. Well, what is the slope of our velocity graph here? It is 0. Rise over run, it's not rising, so the slope is 0. Therefore, we have 0 acceleration. So that would look like that. All right? And same thing applies for this graph. Even though we're standing in negative land, just standing here waiting for someone to come up and beat us up, then it doesn't matter whether we're standing in negative land or positive land. We're still not moving. Our velocity is still 0 with a slope of 0. Therefore, our acceleration is also 0. Now, I drew these a little above and below 0, but I mean these to be on the 0 graph. Sorry, the 0 line, 0 acceleration line, or the x-axis. All right. Well, what about if so up here we were not moving, we were at rest, but what about if we are moving, but we're still not speeding up or slowing down? The slope of these lines are also 0. And because of that, we also have 0 acceleration. And So you may be thinking, well, the position graphs are totally different. They are, but um, there's really, I mean, you can go from position to acceleration, but if you want to keep the same pattern going, you're going to go step by step. So you're going to go position the velocity, and then use the same strategy to go from velocity to acceleration. So looking at position graph, the position graph won't necessarily obviously give you the acceleration graph because we have the exact same acceleration graph for all four of these position graphs, and then you can see the position graphs aren't always the same. So in order to find your acceleration graph, to make a long story short, you're going to want to use whatever your velocity graph is telling you. And we have zero slope, no rise over run. So that means we have zero acceleration. Now, things are different over here. Things are different. All right, let me draw two acceleration graphs. While I'm drawing these graphs, take a look at what's different about these over here. Try to predict what I'm going to draw. All right, time zero acceleration. All right. So, this graph, we determined last time that we were not only moving in the positive direction, but we were also speeding up because the slope of this graph gets steeper. Okay? And that was represented by a velocity graph where the velocity is increasing because we're speeding up. And since we're moving in the positive direction, our velocity is positive. Now, it can get a little confusing here because here I say we're moving in the positive direction. Here I can't say that because, well, in terms of just the disregard. I'm putting my hand. Sometimes I wish you guys could see what I'm doing. I guess I could use a web camera, but I don't want to do that. Mentally I'm covering up the position graph. So this is gone. This has disappeared. Our velocity graph is now moving in the positive direction. Now, when I say it that way, I probably shouldn't say it that way because we're not moving. Well, let's look down at this graph, right? Here, we're obviously moving in the negative direction, right? We're going down into negative land. But let's look at the corresponding velocity graph. The velocity graph is moving towards more and more positive velocities, right? So if I were to say it kind of incorrectly the way I set it up here, the velocity graph is kind of moving in the positive direction, but it's not the actual positive position. I'm thinking of velocity all by itself. And so a better way of saying it is we're moving towards more positive velocities. We're not really moving towards a positive position. We're moving towards more positive velocities. So back up here, we're moving towards more positive velocities. And because of that makes our slope positive. Our acceleration has to be positive. And that would look like this. Now, why is it flat? Why is our acceleration not increasing or decreasing? Because the slope of our velocity graph is not changing. And the acceleration value tells you the value of your slope at that point. So, what do I mean by that? Let's say we're looking at t equals 5 seconds. At 5 seconds, according to this graph, our acceleration is, I don't know, 3 meters per second squared. What that means is, at 5 seconds here, the slope of this line had better be 3, because the value of our acceleration graph tells you the slope at that corresponding time. If over here we look at 7 seconds, our slope is our value of acceleration is still 3. So our slope, let me just use this dot from the last video. The slope of our velocity graph at 7 seconds had also better be 3. Remember, slope is rise over run. So, yeah, in summary, the slope of our velocity graph tells us our acceleration value. Okay, so looking at the blue curve over here, our slope is negative, right? And so our slope being negative, our acceleration has to be negative. And it looks about the same steepness. So let's say the slope here is -3. So our acceleration is going to be -3. And again, it's flat because our slope is not changing. Now, we could take it a step farther and say, if we had a curve like this in our velocity graph, then our acceleration would be changing. And in fact, we do talk about that in this class, whereas in honors physics, we would never go that far. But I'm not going to talk about that in this video. And so going down here, I want a line, and I want this color. Now, even though our velocities are positive, because this is where it gets a little confusing, we're moving in the positive direction, but we're slowing down, right? So our velocity is actually moving in the negative velocity direction towards, I should say, our velocity is getting towards more and more negative velocities. We did stop here, so we're not going into negative velocities, but we're moving towards this negative area on the velocity graph. That means our slope of our velocity graph is negative, and that means our acceleration is negative. So this is a negative slope. This graph is negative. And correspondingly, the slope of this velocity graph is positive, even though we're moving in the negative direction towards negative land. The slope of this graph is positive, therefore our acceleration has to be positive. All right. So this, you can see, I just want to summarize, all of our accelerations are constant. Flat, 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 flat. Flat, 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 flat. Our accelerations aren't all 0. These are non-zero accelerations. On the previous slide, those are 0 accelerations, but they're all flat. So that means constant acceleration, which means all of these graphs can be described with the kinematics equations. So you have to assume that these are parabolas. And so I mentioned earlier I wanted to show you how graphically you can come up with the second kinematics equation. Let me show you that now because it's really cool. So in showing you this, I'm just going to draw a velocity graph. 0. And our velocity graph is going to look like the following. We're going to start at some non-zero velocity and speed up. Okay. Now, I'm going to go into calculus mode. the thing is, I don't want to steal all of the thunder from calculus. If you're taking calculus now, um, I don't want to steal away all the thunder. If you've already taken calculus, you're going to know what I'm talking about. So what I'm going to do is I'm just going to tell you a calculus rule, and you're going to learn the why in calculus. I'm not going to discuss that in this class because I don't really need to. All you need to know is how it works. So in calculus, you're going to learn that the area under a curve, we say curve in calculus, even though sometimes our functions are not curvy, like a straight line, but usually they're curvy, and so we call all functions, at least that's how I learned it, we call all functions curves. So the area under a curve equals the derivative. Let me think about that for a sec. Equals the derivative. No, sorry. Let's go back. I take that back. Equals the integral. Integral of a function. Earlier, I showed you the power rule, right? Where if you have something like something of the form ax to the n, if you take the derivative of that, that becomes n a x to the n minus 1. How this relates to physics is if you have something like x equals 4t squared, you can find the velocity by taking the derivative, and that gives you, using this rule, 8t. So using this rule, I go from this function to this function. Going in this direction is called the derivative, or differentiating. But you can go backwards too. You can go in the other direction. You just do the opposite, basically the opposite of this. You go from here to here, and that's called integration, or finding the integral. So graphically, if you find the area under this curve, let me draw that in. If you find the area under this curve, it will tell you that's the integral, so that's going from velocity up to position. And so that's going to tell you basically on your x t graph, it's going to tell you your displacement, how far you've moved. Something like that. So you've gone from here to here, right? So again, you're going to learn why this is the case in calculus. I'm just telling you the area under the curve will basically move you up. Do I still have? Yeah, great. So the area under the curve moves you in this direction, right? The slope moves you this direction. If you find the slope of this curve, it tells you the value on this graph. That's essentially differentiating. Finding the slope is, at every point, is finding the derivative. So the slope of this graph tells you what this graph looks like. The slope of this graph tells you what this graph looks like. That's, in calculus, differentiating. The area under this curve tells you what this graph looks like. The area under this curve tells you what this graph looks like. That's going in the opposite direction. That's called integration. All right? So let's clear this up a little bit. I don't really want that right now anymore. And let's clear this up. I just want to focus on, and let's clear this out. Can I just Can I just drag? No, I don't want to do that. No. Can I just drag? Yeah, that's what I wanted. Um, Trash. So, I mentioned earlier I wanted to use a graph to prove this second kinematics equation. X minus x naught equals v naught t plus 1/2 a t squared. All right. Let's label some things up here. This is our initial, at t equals 0, this is our initial velocity. So I'm going to call that v0, this value here. And that's going to correspond to this right here. I mentioned the area under the curve tells you, your displacement. That's this piece right here. I mentioned the slope of this curve tells you the acceleration, right? Slope of a velocity graph tells you your acceleration. That's this piece right here. And of course, time, this axis, is represented here and here. So let's find areas. The area under this curve, we can use simple geometry, right? We can break it into two pieces. Let me use a different color. Let's stick with blue, I guess. Yeah, let's use yellow. Let's try yellow. Let's break this graph up into two segments. So here we got segment 1, or piece of the graph 1, and piece of the graph 2. Piece of the graph 1 is a rectangle, right? Piece of the graph 2 is a triangle. Alright, so I said the area under this graph tells us what we need to know. What's the area of this rectangle? Area of a rectangle is length times width, or basically you multiply these two dimensions. And what is this dimension? How long is this? Well, it is the distance from here to here, which happens to be a length of v naught. So area 1, it's going to be v naught length times width. How long is this segment? It's t, right? Going from 0 to t, and it's just t long. So the area of this piece is v naught t. All right. What about the area? What about area 2? This triangle. Well, we end up here, and we can label this velocity v, or v final. In our book, it just says v, right? And the area of a triangle is 1/2 base times height. So 1/2, and our base is t, and our height looks like this distance from here to here, right? Basically v minus v naught. All right, but that's not quite so nice. That's not really exactly what we're looking for. So we can think of it a different way. That's the slope of this line gives us the rise over the run, right? Slope is rise over run. Slope m equals rise over run. let's just write this out. Slope is rise over run. Slope of a velocity graph, we determined earlier, is your value for acceleration, right? Good. And what is the rise from here to here? We just said it was v minus v naught, right? Going from here to here, we've risen how high? This high. And that distance is v minus v naught. Maybe I'll explain this a little better. This from here to here, this whole distance is v, right? And from here to here, this distance is v naught. So to get just this distance from here to here, you have to subtract away the smaller piece, right? Okay, so I think I explained that well. And going back to here, what is the run? The run is this piece, which happens to be time, right? So acceleration is the slope, and that is the rise over the run, v minus v naught over t. We can rearrange this and solve it for v minus v naught basically by multiplying t on both sides. And so we get v minus v naught equals a t. Now we can do a substitution. And replace this with 1/2. Replace this v minus v naught with what it equals over here, at. And if you simplify that, you get 1/2 a, and you have t times t, which is t squared. Okay, and so this is the area. This is area of piece 1 and area of piece 2. To find the total area underneath, you can simply add the two together, right? So we're going to add the area of piece 1 and the area of piece 2. And let's take a look at what we were looking for. Here's area of piece 1, v naught t. Whoa, v naught t. Here's the area of piece 2, 1/2 at squared, and we add them together. And that gives us our displacement. Voila. So graphically, I've just shown you how to derive this equation, which is a different way than deriving it from the equations in the previous video. That's beautiful. This, to me, is beautiful. I love it. I love this stuff. And so, whoa, 28 minutes. Time flies when you're having fun. I'm going to end this video here and see where we go from there. All right, thanks for watching.